In this video, we're going to take a closer look at how we can move blocks around to different sides of our summing junctions. And so a good question that you should be asking yourself is, why do we want to be able to do this? And the answer is we haven't really given a good reason yet. We're going to get to it in a few videos from now. But it turns out that we're going to have sort of three common forms or three common topologies that we're going to use as we're reducing our systems. So three common topologies used to reduce our systems. And so just to list these sort of as a preview here, the first one is going to be our cascade form. And so we can think of this as items being in series. The second is going to be our parallel form. And then the third is going to be something called our feedback form. And so as I mentioned, we're going to come back in later videos and we're going to look at all of these forms in detail. But before we get to that, we're going to have to be able to adjust our block diagram a little bit. And one of those things is going to be moving our blocks around to different sides of summing junctions so that we can get our various parts of our system in one of these three forms. And again, we'll see a lot about this later, and we'll look at several examples as well. But first, let's talk about how we can move blocks around our summing junction. So let's put a summing junction here, and let's say we have a block G of S over here on the right side of our summing junction, and this is our output C of S, and we have some input R of S, and some other input X of S, which is either being subtracted or subtracted or added, excuse me. So let me make this capital X since we're in frequency domain. And so let's say we want to move this G of S over to the other side because maybe we need to get it out of there again so we can get it in one of these forms, or maybe on the R of S or the X of S side, we need it to be able to be in one of these three forms here. So what we can do is we have to put it in both of those branches on the other side of the summing junction. So we can say that this is equivalent to, and let's put another summing junction here. So it's equivalent to having a G of S here as well as a G of S here. And into those we still have our R of S on the top and our X of S on the bottom. And then this is our C of S over here. And so to confirm this equivalency, what you can do is sort of trace our inputs to the outputs. So for the left side, we can see we have X of S coming in, R of S coming in. Let's say that X of S is being subtracted. So what we can say then is we can say that our C of S is equal to, and let me move this a little bit so we're not running into the right side there, is equal to G of S multiplied by our R minus our X. And so of course we want to preserve that relationship as we move our blocks. So if we come over here and we now evaluate this system on the right side, we can see we have R times G of S being combined with X times G of S. So we end up with our C of S over here. So C of S is now equal to R of S times G of S minus X of S times G of S. And so of course we can factor out the G and we get the same thing that we had before as we would expect. So that's how we would move a block from the right to the left. Let's say we wanted to go in the opposite direction. So here's our summing junction. And so now let's say we initially have some block G of S over here on one of the input sides. So now this is our C of S. This is our R of S, and this is our X of S. So if we want to move that block to the right side, we could say that that is equivalent to, so here's our summing junction again, and so we're getting it off of the left side, so we're just going to have R of S here. So as you might imagine, of course, we're going to have to put a G of S block on our output before we go to C of S. But we're also going to have to add a block here that is 1 divided by G of S. And so sort of the reasoning behind that, without sort of tracing our inputs all the way through, is that here, of course, our x is just going directly to c of s. It's not being multiplied by g. Whereas here, if we had x of s right here, it would be multiplied by g now. So we have to have this 1 over g to cancel out with that g of s that it sees here. So again, we could go through the same type of procedure and we could figure out c of s in both cases. I'll leave that as an exercise to you, but doing so should confirm this equivalency shown here.